Davis, and I'm going to be talking today about the computing cluster we built at work, and how that went, and how we used FreeBSD in the process. I'm going to start with an overview of the cluster, the hardware, basic software, and then talk about some design issues, some design decisions we made, and how they played out, and then look at some lessons learned, and then finally a very brief look at thoughts about what I would do if I were going to do it again. So history, we started back in 2001. The primary motivation at the time was that the GPS satellite program that we support needed to make decisions about where to put new satellites. As they're built, they launch a couple a year to keep the constellation up and running. And so they need to decide, where do you put the satellites so that when one fails, we have the best system remaining, and base that on things like how old the existing ones are. And so that's there. But it was actually intended to be a corporate resource with a diverse set of users. So the GPS people were the ones who needed it, but we had other users across the company because we do virtually every sort of engineering related to space systems. So literal rocket scientists, sensor people, all sorts of things. And so we had a whole lot of different users, which meant that we had to make a number of compromises along the way. So basic hardware in the system, we have 352 dual processor nodes. With the addition of the quad-core Xeons a couple weeks ago, we're now up to almost 1,400 CPUs, or CPU cores, so quite a large system. And I'll talk more about the exact processors later. They have some variable amount of RAM. I think this is actually wrong now in that they're all at least 2 gigs of RAM, and almost all of them are 250 gig disks. And then we have a number of core systems that do different, perform different operations. Actually, this is slightly out of date in that the Proto system has actually been combined, has been removed. It was an ancient Pentium 3, 1 gigahertz that I finally retired this year. But we have shell servers, an AMD 64 shell server that's not really being used yet because we're not running the nodes in 64-bit mode. A NetBoot server that boots all the nodes are netbooted over NFS with PXE. And we have a scratch volume that's not backed up. And then we have a NetApp that's the user's home directory. And we do back that up. It's just a picture of the machine room, the 2 aisles. You can't, it's hard to see, but over here there's the patch panels that we use. Yes? I'll talk about it more later, yeah. There's some more slides, I think. If not, ask me at the end. And then we have our nodes. The ones here are conventional 1U servers. Those are actually gone, and everything is now some about 18-inch deep nodes. And I'll show another picture of them later. So here's our processor composition over time, and here's this was the beginning of the year, and this is now, and our build up from nothing all the way up, and moving from Pentium 3s to Xeons, and then Opterons, and then dual-core Opterons, and finally quad-core Xeons this year. And then just another graph showing how the growth curve increased much more rapidly. Here we've plateaued in size, but our core count shot up dramatically. So that's just another little graph. Here's our network layout. We have our corporate network here. Off to the side there's firewalls and there's internet and all that. Increasingly inaccessible. And then we have our core systems here. It's all connected together by a fully populated Catalyst 6509 that actually right now limits our size. To go any bigger, we would have to start putting in 10 gigabit Ethernet blades and doing channel bonding between them, which would substantially reduce our our bandwidth in some calculations. So that would be a possibility. And then we've got all the nodes hanging off there with our nice boring naming scheme. So software, we're running a FreeBSD 6.2 release, actually with all the patches as of a couple of weeks ago. We're running SunGrid Engine. This is out of the ports collection. We have a number of MPI implementations. We're using MPitch and MPitch 2 at the moment, and OpenMPI is something we're getting ready to try to deploy. As we're growing larger and larger, we're starting to see fragility in the startup code of these various things. So trying to try some new ones. We've also got a few PBM-based codes. It's a competitive message passing interface to MPI. There's only one implementation, and it's kind of deprecated at this point. We're also doing some Mathematica. We're actually the launch customer for Grid Mathematica. Interestingly, given that it only comes with Linux support, so we're running it under emulation. And then we're running MATLAB as well, although that's just single licenses. So now I'm going to talk about design issues. I'll talk a little about each of the issues, what we did, and how it worked out for each one of them. So first off, operating system. It's one of the two main things you've got to decide when you're putting together clusters. What operating system, and the other big one right at the top is, what processor architecture. When we actually started out, processor architecture was something where you had a little more choice, but I'll get to that in a minute. So we started out with FreeBSD 4. It worked great for many years. We actually never did upgrade during the 5 series. It wasn't a whole lot of benefit for us, but we've gone to 6 now. So the only problems that we had before were basically that the threading, the lack of SMP support in threading meant that applications could not use threads as a way to get better performance. They could only use them as a isolation or as a programming method. So there was one application that was under development, and they had to use a model that was not the one they wanted. But it wouldn't be a problem anymore. We did quite a bit of modification to the boot scripts to get to the point that things were working. The nodes actually did what we want, or the system. One of the arguments for using FreeBSD initially even was that the boot scripts would let us network boot very quickly. I mean, I got them in, I started beating on things and had stuff up within a day, and at that time the documentation was quite a bit more primitive than it is now. But we still did have to make a number of modifications. We do some sort of non-standard things in the node hardware that I'll talk about later. So when you're selecting an operating system, obviously, there's the question of, what do you know? I think that's actually in many cases the most important thing, unless there's a specific feature you really need, because there's just so much spin-up time. And in a cluster, one of the things we found is errors are often really weird, because you're looking at errors that are happening because of the scale, where you've got so many machines, and it's really helpful to have an operating system that you know well. So I think that's really one of the most important choices. But other things to think about, of course, are is there software support? Or in some cases, is there someone I can buy support from so I can sue them? That seems to be a big deal with our management. Now on to node architecture. So here it's a matter of figuring out what kind of nodes are going to work best in your environment. Part of this is your processors. When we actually started out, there's a wide range of choice. The company had actually previously purchased an alpha cluster. We've had since some small Mac clusters, currently PowerPC ones that they're in the process of moving to Intel, and whatnot. At this point, there's only really one architectural game in town, and it's whichever Intel architecture variant you choose, but it's one of them. Itanium is pretty much a non-starter unless you're in a very odd arena. So what we did when we started out is we were basically looking at Intel architecture because we wanted to run FreeBSD, and we didn't want to go off and run something exotic. Also, the alpha cluster had not worked out all that well. the systems were incredibly hot, and a number of them were damaged by overheating at one point, which caused all sorts of pain. So at the time, we were looking at Pentium 3s or Athlons. The Athlon processors were way too hot, and or so it seemed at the time. The newest stuff is all much hotter than anything available then. But we went with Pentium 3s. They worked quite well. We had some problems there, but they weren't really related to the CPUs themselves. It was more build quality issues. We got into trouble with bad hard drives. We ended up with, I think, the first 64 machines all had IBM Death Stars in them. So that was fun. And then we had another problem that over time, initially we had a lot of infant mortality in the power supplies, and every time we shut the system down for some reason, the magic smoke would come out of 2 or 3 of them, and it stopped working. And sometimes there'd be loud bangs, that sort of thing. And then that eventually stopped happening. That went away, but we actually found a couple years ago when we were starting to look at replacing them that they'd actually started failing with very strange failure modes where you turn them on, the lights would come on, the fans would spin, the disks would spin, and they wouldn't post. And it turned out in every case that in almost every case there, if we yanked the power header off the motherboard and stuck another power supply in, it worked. And the conclusion eventually was we think that something was wrong with them, probably leaky capacitors or something, maybe some of the stolen Formula ones. And and as a result, something was going wrong, and the 12-volt rail was low. So those were both sort of odd problems, not related to the CPUs, but we did definitely have some issues there. After that, Intel had continued. The Opteron wasn't out yet, so basically we had no choice. We went to Xeons. They were the NetBurst Xeons, so they worked okay for us, but it was the early hyperthreading implementation that didn't work very well. But overall, they were pretty good machines, good workhorses. We just pulled them out a couple weeks ago, and actually we're going to be putting them in a new experimental cluster. So they're still good today. And then we moved to Opterons. The slide's slightly outdated in that at this point, AMD took so long to get 8 or 4-core systems out that we went with Xeons, the Woodcrest Xeons for the new systems, which we just installed. Now, on to the next part of the architecture. So you've got your CPUs in the system. That's all good. Now you've got to figure out how am I going to have an operating system on these things. And your options are basically you can install it. You can just stick CD in and install it, whatever. I've seen systems that do this, that have done this for quite large deployments, over 100 machines. It leads to interesting scenarios where basically you just never upgrade anything because you can't. There's just no way. Another option is a system where you'll image the disks over the network using sort of a kickstart or jumpstart approach, or you can use some sort of disk image deployment system. There are 500,000 of them out there. Everyone seems to have rolled their own. Or you can do a pure NetBoot system. We've done basically a pure NetBoot system with the small change that we do have disks, but they're only for scratch. They're actually /temp, a local /var, and then swap. And that's worked pretty well. For the net booting itself, the process, we're using sort of the standard FreeBSD diskless boot process, where we've got an NFS server, TFTP server, and DHCP, and we just do a PXE boot. We're using a pretty stock system. Probably the biggest change is that we have a modified version of Werner Losch's disk prep script. He wrote it to prep flash disks for embedded devices, and I hacked it up to add more partition types and more flexibility. So we actually install. So we carve up the disk on the fly. We have a version number. Currently, we're using a G-label to do the versioning. We just change the label. If we don't see the label we want, we just blow the disk away and start over. we do have a policy that we don't do any backups. And in the 4.x version, we were actually, if the disk wasn't clean, we just nufised it. It's vastly faster to nufis a disk than it is to fisk it. So that's what we were doing then. We haven't got that working again, but that's where we'd like to be. Actually, it'll be a little project if somebody wanted to do it. It'd be really cool if you could have a config file on the system in the standard configuration that said, for this disk, if it comes up unclean, just zap it. For this one, do a foreground fisk. For this one, do a background fisk. That sort of thing. That would be a nice feature. I keep meaning to do something about it, but maybe it'll happen. We also did gigabit Ethernet for the network interconnect. Your options there are, you can sort of go with whatever's there. When we started out, that was actually 100 megabit Ethernet. That was what was standard on the motherboards. We had some users who said 100 megs, as much as we're willing to pay for. We're doing loosely coupled applications. They don't do any communication between each other. They ship very small data sets around. So, don't waste money on this fast stuff. And then we had other users who were saying, well, we're doing computational fluid dynamics, and we need, fast interconnects with extremely low latency. Let's buy expensive proprietary interconnects, $1,000 or $2,000 a port sort of things. And GigE was sort of our compromise. At the time, it was about $600, $700 total cost per port. It's interesting to note, that definitely played out well, in that at this point, gigabit Ethernet is free. There's simply no price difference in the large switches. If you buy a 10100 blade, it costs the same, possibly more, since they're obsolete. Likewise, it's on the motherboard. What's interesting is actually 10 gig is rapidly approaching the point where we bought GigE. Right now, it's running about $2,000 a port, but if you look at the trends, NICs are probably going to be $300 next year, and ports may well be below 8. So, that's going to be the next big thing. And given that they've got a twisted pair interface now, I wouldn't be surprised to see them on server motherboards in 3 years. And we went with custom 1U chassis, except for the one Xeon series of Xeon nodes. I think I have a picture, yes. So initially they were 14-inch deep 1U chassis in the form factor. And the Xeons were standard because we bought Intel OEM ones, and they've been quite reliable. We've had very few failures. We've since gone with with a custom front mount solution. And we do, rather than using cabinets, we use telco style racks, as you saw in the picture. That's personal preference sort of thing. I just find it much easier to work in that environment. And with the front ports, everything's really easy. The only thing on the back is some removable fan trays on the Opterons, and then the power. And here, we've got a removable disk. We've actually since switched to a model where it's a custom chassis, but we're using Supermicro disk sleds in the current ones. And then, motherboard and expansion cards. This makes it really easy to do all the management. We're just running cables down from patch panels in the top, and it's quite clean. Not a common solution, but I think it's really, really worked well for us. It really is not adding much cost. If you have a vendor that's willing to work with you, it's not that big a deal. Node configuration management. I've talked about this a bit already in terms of how you boot nodes and whatnot, but the other part of it is how do you, in addition to how do you boot them and how do you keep them up to date, is how do you update the OS? When we were running 4X, what we actually did is we just installed into a chroot, and when we wanted to do an upgrade, I'd just make a copy, change root into it, and do a port upgrade, do a build world, that sort of thing. Worked really well. Makes it really easy to maintain all the hacks you've got in Etsy and everywhere, because you're just using Merge Master and all that. So that worked great, except that I got to 6X. It'd been 3 years, almost 4 years, I think, and I was like, I have no idea what I did here. And trying to figure out what was there was a really annoying process of trial and error. So based on that, and because there are these tools like MeetBSD or some of the Frisbee tools for building images, I decided to try a new approach with 6, which is that I use I scripted the entire thing, so every time we do an update, we create an entirely new image and do a complete rebuild. It's a little more time consuming in some regards and more work to set up, but it records all the modifications. So that's really nice. Right now there's a couple things where we have a couple things that we're not scripting just quite yet. There's a sudo file, config file we're not scripting, and root's password has to be set. But other than that, it's pretty easy, and just works. I mean, the last time I did an upgrade, I just ran the build script, went away for other than fetching dist files because of our firewall and copying them in. It was just a matter of fire it up and forget about it, and came back about a day later, total build time, and it was all ready to go except for those 2 tweaks. So that's worked out quite well. Physical system management. So this is just how do you sometimes you've got to poke at the systems, you got to get to the consoles, that sort of thing. In the initial setup, we had a KVM switch for the core systems. They were systems we'd actually have to maintain hands-on. They also had CD drives and that sort of thing, so it's possible to do anything on them. And then we had serial consoles for the nodes to let us do debugging. That did help now and then. It turned out we rarely used it, and with the particular motherboards we had, the BIOS serial access port was unusable. We actually deployed them with it installed. We thought everything was working. We got reasonably reliable boots at 9600 baud. Any faster, and the systems would hang. And then for extra fun, we found out, oh, well, actually they hang about 1 in 20 times. So, in the lab, it seemed like nothing was wrong. When we put it in the rack, and we had 64 of them, that meant 3 or 4 failed on every boot, and that was not manageable. So we dragged out the cart, came with the keyboard and mouse and everything, and monitor, and changed all the BIOS settings by hand, and went with that. So that was a pain. What we switched to now, we've got a VNC-based remote KVM for the core systems. It also has a monitor locally. It's quite nice. It's a little Lantronix thing. And then we have rack mount LCD monitors and keyboards in all the node racks. So we don't have to go find where somebody put the cart and figure out where a monitor is and all that anymore. That's actually turned out to be a pretty good investment. It's about $600 a rack, so less than the cost of the rack itself in additional cost. And so that was actually a good move, I think, and we're moving to do that at to retrofit the old racks. So lessons learned. I'm going to talk over some of the lessons that I learned in the process. I will say there's nothing shocking about any of these things. They're not big, huge things, but I think they are useful to relate. There's 2 types of them. There's technical lessons and then non-technical lessons. How in dealing with the user population. The user ones were all things we should have anticipated and sort of didn't. I've alluded to this already, particularly in the BIOS issue, but one thing to watch out for in a cluster is uncommon events. Well, you've got so many more machines that they become quite common. We fairly commonly, with most of the hardware batches, will lose. It's not uncommon to lose a machine across the whole cluster every time we power cycle. You got to figure that's not that unreasonable if we only do it a few times a year, but that if a machine's going to die randomly sometime over 5 years, a good portion of them are going to fail in a 300 node system. So that definitely happens. Something to watch out for. So it does mean though that you have to be very careful when you're diagnosing problems that come up, say at boot or whatnot, that it might appear fixed in the lab, but you've got to try it a lot of times to be sure, because once you get into the whole cluster, you'll start to see it. We also, so another example actually is PXE boot failures. So there are probably multiple causes here. In the initial system, the biggest thing we saw is actually that the system was, even with spanning tree turned off on the switches, we'd have a race between the PXE boot timeout and the negotiation with the switch. And so some of the nodes, which maybe were running a little fast or something, would tend to would fail a small portion of the time. We had a couple that were really close, and they'd only boot about maybe 1 out of 3 times, and they'd drop through to the disk, and then they'd say no operating system and hang. Our workaround in that case was, I think, slightly clever, which is that we threw up the partition with the partitioning tool. We install a FreeDOS partition with just a reboot program on it, and so the nodes just try again every time. That worked well, except one time I had 2 nodes, and I was planning to do some experimentation, so I reconfigured them in the DHCP config, and then done it wrong, so they weren't actually booting. And then I got distracted and forgot about it for a couple of months, and I came back, and the network interfaces did not negotiate anymore. Somehow, something had actually failed in the process of repeatedly rebooting, and you could leave them plugged in for an hour, they just never sync. So that was an interesting failure, and I didn't realize that could happen, but apparently it can. We also had the disk failure problems. It's worth also keeping an eye out for possible systemic failures. That at some level, you expect to see things a little more often than you would with a single system, but the disks were in fact Death Stars. And the power supplies clearly, in retrospect, were defective. They should not have all failed to the point that the system didn't boot within 5 years. That just shouldn't have happened. And so, that's also something to watch out for, is that these things that are becoming common may in fact be systemic. And because, if they're not catastrophic failures, that can be a big deal. So you got to keep an eye out for that, and hopefully catch it while you're still under warranty. Actually, there's an interesting story of one of the national labs in the U.S. They actually got a warranty replacement of 16,000 disks, the entire batch for a large multi-thousand node cluster, because the drive lubricant was bad. Fortunately, with their purchasing power, they were able to, after a year, convince the manufacturer that indeed the drives were out of spec. Now, another small one, Neatness Counts. I really ought to have a picture of one of our ugly racks, but poor cable management makes your life really painful when you're trying to do maintenance. We had one of the racks that was installed by one of our engineers who's just notoriously lazy about cable management. And so we got it in, everything worked fine. And then every time we had a failure, we would spend a lot of time cursing him when we had to dig the cables out and figure out what was going on and get everything replugged. And so it really does matter. I would say it is a good argument for blades. Perhaps the only good argument for blades at this point. You rarely can get enough density to make them worthwhile, but the maintenance aspect is pretty nice in terms of clean cable management, reduced cable count. Of course, that also reduces your bandwidth, which is why I don't think they're very good. So another issue we've ran into, not too big a deal, but it's something to watch out for if you're using FreeBSD, is that the world is not all Linux box, despite what all the software authors think. So we had to port some applications. The good side for everyone here is thinking about a FreeBSD cluster. Well, we've already done most of it. Except Globus doesn't work at the moment, so I owe Chris a fix, as usual. Another issue is some applications are Linux only. For Mathematica, we've had pretty good luck running it, just running it under emulation. As I was saying, we are the launch customer for Grid Mathematica. It gets a fair bit of use, so that's worked quite well. The scripts need a little modification, and I've got a port I keep meaning to finish to make it a little easier. MATLAB worked pretty well. Last time I tried it, we couldn't get the GUI up, but that was okay for the job that they were doing. And it turns out MATLAB licensing is really horrific. So in practice, it's not very useful on the cluster. The company just bought a complete site license, but it doesn't cover this application. So there you go. The one thing we are probably missing that is a problem for us is total view. It's a parallel debugger. It's quite expensive, but it's a huge time saver for debugging certain kinds of problems. And unfortunately, it's a debugger, so it's quite tied to the operating system, and we really can't run it. One issue we have had is that sometimes it's hard to tell where a failure is. The example I have here is the lamb MPI, which for quite some time the version imports built, but it just blew up every time you try to run it. It immediately segfault on any app. And it's hard to tell, what went wrong. Is it their fault? Is it our fault? What's going on? Most of the time I would say, though, that, even with Linux apps, it's usually not FreeBSD's fault, remarkably enough. Mathematica, I've dealt with Wolfram Research on many issues. At this point, I just lie to them because it's never been the case that FreeBSD was at fault. It's always been a red herring, and so that's. But it is something. It is sometimes a problem. Automation is key. Should be obvious, but it's worth hammering this one home. Doing anything on all the nodes is just completely impractical. As I mentioned, I've seen people out there where the only thing they could do was log in and work on the systems. They could do a little remotely, but they didn't really have tools to do it. So you want to avoid it. The reality is we've actually had to go in and touch the BIOS on every machine except the current one. So that's kind of a pain. But if you could, for everything else, we've managed to avoid it generally. We actually even were able to, for instance, wipe all of the disks at one point due to a data leak. So there's plenty of stuff that you could do that you can automate. The other thing to think about is monitoring. If you don't have good automated monitoring, the way you find out about problems is the users tell you about them, and it's much better, I think, and much more pleasant if when the users complain about the problem, you can say, yeah, we know. It may not be the answer they want, but at least you're not caught blindsided, and you're as you're heading out the door to go home with some problem that cropped up in the middle of the day. So it's quite important. And it is worth pointing out that Unix tools are great. In specific, Xargs is your friend. Learn it, love it. Just a little example. We're actually not using this anymore because we're using PSSH, it's a parallel SSH client, which actually was a good example of how the world is not a Linux box. I can't figure out how the code could possibly work on any operating system without patches. Yes?
Your access all nodes is having private key on numbers and cost. How you are go to the node because you are remote command of the SSH. So from the one host we have all operating keys from all other hosts. But you don't have to give a password.
Oh yeah, in this case I'm using an SSH key, so it's all key based. There's an agent. In our particular setup, all the admins are in the root's key file. You have to trust the network completely if you're running NFS and NIS, so not a big deal. So now some user-related lessons. One of the big things is our users have a job to do. They are experts. They are not computer scientists. They are not programmers. They do write a lot of code, which has interesting results and often very interesting formulations. It's just something to keep in mind, and it's always sort of a challenge because they've got to get this done, but they don't want to change anything in their strategy or change how they write code, change anything, and it's quite a fight sometimes to get them to do the right thing. So one of the problems we had early on is that we were planning from the start to use a batch scheduler, but right at the beginning we had to show results because we were only allowed to buy 8 nodes out of 100 that we needed to be up to fairly quickly, and so we had to show results. So we didn't put a scheduler on, or we let users get going while we waited to figure out which scheduler you're going to use and get it ported and all that. And then because we had we chose wrong the first time, the first scheduler just was totally unstable. We're pretty sure that was not FreeBSD's fault, but or the fault of the FreeBSD port, but that was an issue. So it took us quite a while to get to the point where we had a scheduler. And then we made the mistake of assuming that users would see the light and they would say, ooh, the scheduler gives me all these good things. I know when my jobs are done, I can start them up and I can go home and not have 8 terminal windows open monitoring all my jobs. But the reality is they didn't. And so it was quite painful to force them to use the scheduler. Eventually we did it, and actually the way we did it I think is useful to keep in mind, which is that we also did it in conjunction with the upgrade to FreeBSD 6, because we had some new nodes come in and they wouldn't boot under 4. So we did this in-place upgrade. We put in new core systems, and we started moving nodes over. And at the time, we had one big user who had to have tons of cycles. They had this big deadline. They were presenting to Congress. So they really needed to get this done. So we said, we've got these new nodes over here. All you got to do is use the scheduler. And they went along, and we just made everyone, we started moving things over slowly, one at a time. And that did work, but it's interesting. One other observation we've had is extremely uneven user demands. We have one user who's used about half the system. The top 5 users out of over 100, nearly 150 now, use 95% of the CPU. So just, I think that'll vary by site, but that was an interesting thing we saw. So some thoughts on a future cluster. Disks were the top cause of failure that we can get rid of. Can't really do anything about power supplies, although other than switching to blades perhaps, so you at least have less of them. But if we could get rid of the disks entirely, I think that could work well. And with current memory sizes and memory prices, I think it's probably a practical approach. It's something I would like to do in the future. I'd like to step up to a faster network. Probably, if I were doing it today, if I were planning to buy something a year from now, I would almost certainly spec 10 gig. Today, it would probably double the total cost, and the largest switches available aren't very big.
What stuff like InfiniBand or Marinette?
What?
What stuff like InfiniBand or Marinette?
So Marinette, I probably wouldn't bother with the 2 gig Marinette, which is pretty cheap. The other stuff has pricing similar to 10 gig because it is in fact 10 gig, except for if you plug it into a Marinette switch, it performs better, or it uses a Marinette protocol at level 1. Yeah, we've looked at it a little. Right now, if you want to run FreeBSD, you could run Marinette, but you can't run InfiniBand. That is a weakness for us at the moment. Some of the work Kip Macy's doing with 10 gig Ethernet, though, actually is gonna help us there because he's working in Open Fabric. So yeah, I mean that would be something I would look at today for our application mix. We have a few users who really do want that very tight coupling, but it's not a tremendous number. So we would probably, I think I probably would do, if I were buying today, I would do gigabit, and what I've been doing on the hosts is ensuring we had a PCIe slot, so we can potentially add a new interface. I think in a year, it would probably be a good move unless you really, really didn't need it to do 10 gig, because I think by then you won't be much over $1,000 a port total cost, particularly with 10G-based T, burn Cat 6A. So I've also been thinking that we should look at doing blades. I think for remote sites in particular, I think it's very helpful. The company is actually planning to build 2 new clusters. They unfortunately will be running Red Hat, and they're sort of out of my hands. I'm trying to stay as far away from them as I possibly can. For there, I was suggesting blades. We ended up going with 1U systems again on that system, though, because our VP had severe price shock when I showed him the quotes. Gave him a set of options of 1U systems, some IBM blades, because I think it's the H series is the only blade out there that I know of where you can actually get full bandwidth out the back. And then I had priced in Penguin computing blades, which gave you amazing density, 48 CPU packages in 4U. It also ran $1.5 million a rack. So a substantial chunk of change. And so this sticker shock quickly shoved them towards one use, but I did think blades were possibly a good idea there. So I say reconsider OS choice. The company is reconsidering the OS choice. I think actually with FreeBSD 7, particularly once we get dtrace hopefully in 7.1, I think it's going to be unbeatable. We're going to be in really great shape. I need to find some time to work on some more of these HPC workloads and start working with people like Chris and Jeff Robertson to figure out exactly what we need to do to really max out our performance there. But I think it's we're really in great shape. And one thing actually that we will be changing with the new clusters the company's buying is right now the people running it are me and a couple of my coworkers. We're really computer systems researchers, and I'd really rather not be doing quite this much administration. So, conclusions overall, the cluster is in daily heavy use. Many times a year, it's running flat out 24/7. And the rest of the year, it's pretty much full, at least during the day. The users still haven't quite got the hang of submitting jobs that run overnight. But with increasing use, I think that'll happen more and more. I think FreeBSD has served us very well, both as a computing platform and as a research environment. And one thing actually that I found very informative about using FreeBSD is because it wasn't Linux, I couldn't just grab this cluster distribution CD and get going. So I actually had to see what all the pieces were and put it all together myself. And it was fun, and not all that hard really. But it was very useful in that regard because it wasn't this magic box over here. I would say for a FreeBSD shop, FreeBSD is clearly your choice unless some key piece of software won't work or some key piece of hardware just can't be supported. And I would say in general that FreeBSD is an excellent choice for a cluster. So yeah, that's the end of that. So if anyone has any questions, I'd be happy to take them.
Do you have any disk performance issues in your cluster? I mean, all systems are maximally NFS shells per system.
Yeah, so disk performance, we occasionally have some problems with the NFS server. Most of it is actually sort of the inherent limitations of NFS, where you get into problems where if you have too many people hitting the NFS server too hard, you start dropping packets. And once that happens, everybody starts retransmitting, so you get even more bandwidth, and it just sort of spirals out of control. It's not usually been a problem, though we did have one user with a particularly badly behaved application where they did take out the NFS server, and performance was just atrocious. And the solution in that case was we had them submit less jobs at a time, and it worked. It's not ideal. One thing that actually probably should have been on the considerations is that I think that for a lot of clusters, probably the way to go is to look at an alternate storage technology, most likely one of the clustered storage solutions, either a proprietary system like Isilon or NetApp or Panasys. By the way, they're all FreeBSD or based, or using Lustre or something like that. But for us, we've done all right with just NFS most of the time. Other questions?
So the root file system of all nodes is known by NFS.
What?
The root file system of all nodes that calculation are known by the NFS.
Yes.
And the NFS server is NetCompiler.
That server actually, the actual node roots are mounted on a FreeBSD box with a cheap Adaptec RAID controller. It's actually, that system never sees appreciable load. The one change we did make is we bumped the number of NFSDs up a bit. Once we got up to 20, we started seeing the lowest one never got dispatched. So in practice, it doesn't seem to be a big deal. When they all come up, I think they probably boot a little slower, but BIOSes take so long to boot, I don't think it's even noticeable compared to the rest of the speed issues.
How the cluster is scaling?
What?
How the cluster is scaling? How much nodes can you add to it, and how they will behave?
It depends on your application, almost entirely. For some applications, you're going to be limited by the largest switch that you can get full bandwidth on. For other things, so typically that's been in the mid-hundreds of nodes. With Sun's giant InfiniBand switch that they've announced, that number goes way up. But for other applications, they're totally uncoupled or loosely coupled. Your biggest issue is just general back and forth maintenance bandwidth, and you can scale to thousands of machines. There are clusters over 20,000 systems. Some of the U.S. labs. I mean, those people build computers on an acre scale with megawatt, tens of megawatts of power consumption. So you definitely can go that big. It's just a lot of work and a lot of money. Anything else?
Do you use some I/O multi-pathing or IP multi-pathing solution for each node, or is it a single connection?
It's a single.
There's some redundancy? Or
there's no redundancy there. We haven't really had any significant failures. We've occasionally found a bad port, but they're pretty rare. And the switch, we've had ports that were dead on arrival, but we've never had a port fail in operation. So it hasn't been a big issue. Anything else?
Do you do any power management on those nodes now in the cluster? Or maybe it's not an issue in your company, I don't know.
We probably should be doing some power management. At this point, they just run flat out all the time. So what we really ought to be doing is having the scheduler at least be smart enough to, tune the power down. But at this point, we don't actually do anything. I don't get billed for the power, so I don't worry about it very much. The thing sits in a 15,000 square foot machine room, so.
Dziękuję.